So we've looked at scatter plots, and we've looked at how you can look at relationships between two numerical variables. But rather than just guessing or trying to intuitively understand a relationship between two numerical variables based on a scatter plot, we want to know, is there a way to calculate just an overall measure of association between two numerical variables rather than just looking at a graph? Well, there is. The idea behind this set of topics is that we're going to quantify a relationship between two numerical variables. The two most commonly used measures are covariance and correlation, right? To put another way, we can say that so far for numerical variables, we've looked at summaries such as the mean and standard deviation, and those help us to understand one thing, but covariance and correlation tells us, both of these tell us how one thing relates to another, how one variable relates to another variable. So besides scatter plots, we can use these measures of association. We're first going to look at this idea of covariance, and then we're going to use covariance to understand correlation. You can think of correlation as an improved version of covariance. So let's look at our data set of obesity, but this is a slightly different data set. Rather than looking at US states, we're just looking at a set of people, and we have around several hundred people here, and the data points here are individuals. They aren't US states. And we just want to know, is there a relationship between people's body weight and their body fat percentage? So in this case, the variable on the x-axis is your weight, and the outcome is body fat percentage. And looking at the scatter plot, you can see that there's some suggestion of a positive linear relationship. As people's weight goes up, their body fat percentage tends to increase, and vice versa. This is what our data set looks like. We have two columns, one for body fat percentage. So you can see we have values of 32, 22, 21, and then we have a variable for how much each person weighs in pounds. Again, we like to index the rows of our data set. So in this case, we like to say that each row has I equals 1 to n, the total sample size. And it's often useful to index pairs of points. Again, so for person I equals 6, their value of x is 22.6% in terms of their body fat percentage, and they weigh 198 pounds. So we like to refer to pairs of observations, pairs of numbers. For the summary statistics of this data set, we can see that body fat percentage on average in the data set about 18.6%. And you can see that there's some spread there, a modest amount of spread, with the standard deviation being 8 percentage points, and the median is pretty close to the mean here. And we can also see that the minimum and max, the smallest body fat percentage in this data set is 3.7%, the highest is 40%. So you can see that there's some degree of variation. For weight in pounds, our y variable in this case, you can see that the mean weight is 177 pounds, the median is pretty close, 176, and then the range is from a minimum of 127 pounds roughly, and the maximum is about 262 pounds, give or take. When we look at our x variable, the variance is simply the standard deviation squared. So when you take 8 percentage points square, you get this measure of variance of 64. And that gives you an idea, it's sort of an overall measure of the amount of variability in body fat percentage in our data set. For the variable of weight in pounds, the variance is the standard deviation squared again. So it's 29.5 squared, which is 870. So we have a variance of y and a variance of x. We have two measures of variability. But when we look at covariance, what we want to know is what's the covariance of x and y. We have the variance of x, we have the variance of y, but how do they covary together? How does x relate to y? How does the variability in x relate to the variability of y? That's what covariance is all about. So let's look at our data set again. We have the scatter plot that suggests a positive linear relationship. And it does appear that there's this relationship. And it appears that it's roughly linear. Even though we don't fit a line, you could imagine drawing a line through the pattern of the data. Basically, covariance and the related measure of association correlation, what they do is they numerically summarize the strength of a linear relationship between two variables and the direction of two variables. But we'll see in just a moment that covariance has its limitations in respect to a measure of association. Correlation is an improvement. So we will explore that idea of numerically summarizing the relationship between these two variables. But let's again look at this example where weight is our x variable and body fat percentage is our y variable. So we have these two variables, and what covariance is asking is y larger or smaller when x is larger. The shorthand for covariance is, as we've just used just a few moments ago, we use this COV, x and y. It's just shorthand for covariance of x and y. And the way we interpret covariance is that if covariance is greater than 0, then it suggests a larger x value is related to a larger y value, and vice versa. If you have a larger y value, that suggests a larger x value. A covariance less than 0 suggests that if you have a larger x value, you will have a smaller y value, and vice versa. If you have a covariance of 0, that suggests that there's no linear relationship between these two x and y variables. We can also look at the formulas for covariance to understand what's going on. If you have a sample, recall that we use a slightly different notation than we have a population. So if you collect a sample of data, the covariance between x and y is given with this formula. It's denoted by S subscript x, y. That just is the notation for the covariance of x and y. And you can see that what we're really doing here is we're taking what is essentially the average of what's known as the cross products of x and y. The units of covariance are in terms of x and y. So in this case, our x variable is body fat percentage, and our y variable is weight in pounds. So the actual units are body fat percentage times weight in pounds. The covariance for population has a very similar setup, just a slightly different notation. Instead of S subscript xy, we use lowercase Greek sigma, because for population values, population parameters, we like to use Greek symbols just to make clear whether we're dealing with a population or sample. And we use capital N to refer to the overall population size. And then what we're doing is we're using values of mu, the population mean of x, and the population mean of y in our calculation. But substantively, it's again the average of the cross products of x and y, which we'll talk about in just a moment what that really means. And the units again are in terms of x and y. So again, the covariance of x and y, even if you have a population, it's body fat percentage times the weight in pounds. Now, when you're looking at this formula, you see that there's this giant Greek letter sigma. Okay, that doesn't refer to a population parameter. It refers to a shorthand. It's a very convenient bit of notation, and what it means is capital S sigma. It means summing things up. So suppose you have a small data set of values. We have a data set of 4 little observations. So we might label x1 equal to 2, x2 equal to 5, x3 equal to 4, x4 equals 1. So we have these 4 sets of values. You might want to know, well, what is the sum of all these variables? You might say you could just write out each value. So x1 plus x2 plus x3 plus x4, that's 2 plus 5 plus 4 plus 1, that equals 12. You can write everything out like this, but there must be a better way, and there is in fact a better way. It's called the sigma notation. The Greek letter sigma, it just means to sum up. And what do we sum up? We sum up whatever appears after the sigma. So in this case, sigma, what we're summing up is x subscript I. What this is telling us, just sum up the values of xi. If whatever appeared after xi for xi squared, you'd sum up the values of xi squared. So anything could appear after the sigma, and the point is you're just summing up whatever is after that sigma. We also like to clarify the notation for sigma a little bit further by putting notation above and below. So we like to index the values of x that we're summing up. So what this is telling us is it's telling us that what we're doing, we're actually summing up the values of x from I equals 1 to n. So if your data set consists of an overall size of 5 values, 5 rows, 5 observational units, you're going to sum up values of x1, x2, x3, x4, x5. You're going to have 5 values you're going to sum up together. The reason we do this is that in some instances, you may not sum up all the values of x. You might sum up from I equals 1 to 3. So you might just sum up the first 3 indexed values of your x variable. But typically, we will sum up the values of all rows of our data set. So we'll go from I equal 1 to n. Again, all we're doing here is we're doing a shorthand for summing up a set of values. So let's suppose n equals 4. Our sample size is 4 in this case. And suppose we have xi values of 2, 5, 4, and 1. All the sigma notation is telling us is to, in fact, add up x1 plus x2 plus x3 plus x4, where x4 is the last value since our sample size is 4. So we add up 2 plus 5 plus 4 plus 1, we equal 12. Right? That's all the sigma notation is telling us. What it is, just to recap, sigma is telling us what to sum up, what to add up, and in this case we're adding up the values of x. And it tells us what value of x we start with. So we start with that value that's indexed with I equals 1, and we end with that value of x subscript n. So in this case, since our sample size is 4, we have x subscript 4. And we add up those values, and we get 12. So let's look at the formula for a covariance of a sample. The sample covariance is given by this formula, which is just the average of the cross products between x and y. Now you can see here that the sigma, in this case, it's telling us to add up what's known as the cross products between x and y. We're supposed to add up x minus x bar times y minus y bar for each set of observational units in the data set. So if we have 5 rows in our data set, if we have 5 different observational units, you're going to have 5 different values you add up for those cross products. So let's go through a sample calculation so you can really see what's going on. The first step, what you want to do is you want to subtract the means from each of your x and y values. You want to demean, okay, each of your x and y values for each row of your data set. To put another way, what you're doing is you're changing your x and y variables into distances or deviations from the mean. Then what you do is you multiply these deviations for each row or each individual in your data set. So if you have 5 people, you're going to have 5 different cross products that you want to add up together. And then what you do is you take these cross products, you add them up, and you divide by n minus 1. In essence, what you do is you subtract the means from your x and y values, you multiply these deviations together, you add them up and divide by n minus 1. So let's look at a sort of sample data set here. In this case, we have n equals 5 rows. Let's say we have 5 people, we have an x variable, a y variable, and on each of these people we have different values. So the first step is we want to subtract the mean out of x and the mean out of y. What that's going to do is it's going to re-express x and y in terms of deviations or distances from the respective means. You're going to see if people are above or below the mean of x and the mean of y. So let's first calculate the mean of x. You add up all the values of x and divide by the sample size, which is 5. And we get a mean of x for 4. That's sort of a measure of central tendency for x variable. For the y variable, we add up all the values and divide by the sample size, which is, again, 5, and we get this mean of 6. Right. Then the next step is to take these raw values, subtract out the mean of x, and subtract out the mean of y. Again, the mean of x is 4, and the mean of y is 6. So that's what we do here. You can see for that third column, what we're doing is we're taking out the mean of x for each of the raw values of x. So 2 minus 4 is negative 2. 4 minus 4 is 0. 9 minus 4 is 5. 5 minus 4 is 1. 0 minus 4 is negative 4. So what that third column is telling us is it's telling us whether each person's value, the raw value of x, are they below or above average? So that first person has a raw value of 2 on the x variable, and the mean is 4. So that person is 2 units below the average. The next person has a raw value of x of 4 and the mean of 4. So that person has the same value as the mean, and so that person has no deviation, no distance from the mean. For that third row, you can see that that person is 5 units above the mean. The next person is 1 unit above the mean, and that last person is 4 units below the mean. So you can see that we've re-expressed our x variable in terms of, is that person above or below the mean of x? We've re-expressed it in terms of distances or deviations above the mean. We've done the same for the y variable. We've just taken each of the raw y values for each person and subtracted out the mean of y. So 5 minus 6 is negative 1, 8 minus 6 is 2, 3 minus 6 is negative 3, 6 minus 6 is 0, 8 minus 6 equals 2. So we can see that that first person is 1 unit below the mean, second person is 2 units above the mean, next person is 3 units below the mean. That fourth person is simply right on the mean, so they have a y value that is the same as the mean. And then we have a person with a value who is 2 units above the mean. Again, we've just re-expressed our x and y variables by subtracting out the mean, and you can say, well, some people are above and below average. Right. Then the next step is to calculate what is called the cross products. It's called a cross products of x and y because we've demeaned x and y, and we just multiply these deviations together, right? That's a product is simply the result of multiplying two quantities together. We call them cross products because we're using values of x and y. So that first person is 2 units below the mean of x and 1 unit below the mean of y, and you multiply those together and you get a value of 2. For the person in the second row, that person has a value right on the mean of x and 2 units above the mean of y, and you multiply those values together and you get a cross product of 0. In a similar fashion, we get a cross product of negative 15, 0, and negative 8. So each person has a different cross product. Then what we do is for step 3, we want to calculate the average of the cross products. So you add up the cross products for each person in our data set, and we divide by n minus 1, since this is a sample of data. We're treating it as a sample of data. So you can see that 2 plus 0 plus negative 15 plus 0 plus negative 8, that will give us negative 21. That's the sum of the cross products. That's equivalent to using the sigma notation. That's all the sigma notation is telling us to do. It's telling us to add up each of those 5 cross products. And then what we do is we divide by n minus 1, which in this case is 5 minus 1, and we get negative 5.25. That is the average of the cross products for x and y. That is the covariance for this sample of data. Now you might ask, where does this negative sign come from? What does this negative sign mean? Well, let's look at the formula for a sample covariance. You can see that we have this value of 1 divided by n minus 1. That is always positive. As long as you have a sample, you're going to have a sample in which the number of people is positive. So you're going to have a positive value for that first term. But keep in mind that sometimes cross products are positive, sometimes they're negative. So you should ask, what does it mean to have a positive or a negative cross product? What's going on here? Because the cross products, that is where we actually sometimes get a negative value or positive value. And when we take the average of the cross products, there's something in that calculation that is giving us a negative or positive covariance, or in fact a 0 covariance. So let's look at what a cross product means. Here is the scatter plot of our data. You can see we have an x-axis and a y-axis. The origin is in the lower left-hand corner. So you can see that x goes from 0 to positive, and then 0 to positive values for the y-axis. So we can locate each point in our data set based on its relationship to the origin. So we might say that this value, okay, it has a positive value of x and has a positive value of y. Right? But when we talk about covariance, keep in mind that when we calculate covariance, what we're actually doing is we're subtracting out the mean of x and we're subtracting out the mean of y. To put another way, we should rethink of, instead of locating our data points in relationship to the overall x and y axis, we should locate our data points in relationship to the mean of x and the mean of y, because that's what covariance is really doing. So here I've labeled the mean of x and the mean of y. And then you can see each data point can be located not based on the raw x and y values, but you can locate each data point in reference to its deviations with respect to the mean of x and the mean of y. So for example, this data point, you can see that even though overall it has a positive x and a positive y value, in relationship to the mean of x and the mean of y, it's, in this case, it's actually below the mean of x and it's above the mean of y. So this person has an x value above the average and an x value below the average and a y value above the average. And when you multiply a negative by a positive, you get a negative cross product. A negative times a positive will always give you a negative value. But let's look at this person. This person is below the average of the mean of x, but actually has an above average value for y. So you can see that, again, you multiply a negative by a positive, and you get another negative cross product. For this person is below the average of x and below the average of y. Two negative deviations. This person is below average in both respects. However, when you calculate the cross product, when you multiply these two negative deviations together, you get a positive value, because a negative times a negative equals a positive. When we look at this observation and we locate that observation in reference to the mean of x and the mean of y, you can see that a person is above the mean of x and above the mean of y in terms of those averages. And when you multiply those two deviations together, you get a positive cross product. Finally, for this person, you can see that this person is in fact above the mean of x and below the mean of y. And again, we have a negative cross product, because a positive times a negative is in fact a negative value. So overall, kind of tallying up what we've calculated, we have 3 negative cross products and we have 2 positive cross products. So you can just summarize it using this sort of pattern. We have 3 values that entail some combination of a negative and positive value. And then we have 2 observations in which you're multiplying either a negative times a negative, which is a positive value, or a positive times a positive value, which of course is a positive value. There is a pattern here which should be apparent. Right? We can label each of these regions of some scatter plot into regions 1, 2, 3, and 4. And each of those regions has a different set of cross product values. Okay? In general, we can say that region 1 is going to have cross products that are positive, and region 3 is going to have cross products that are positive, because a negative times a negative is a positive value. Regions 2 and 4, however, are going to have cross products that in fact are negative. What this is in essence telling us something about the relationship between x and y. So let's look at a scatter plot that we would say this looks like a negative linear relationship. Well, in fact, if you look at the number of data points in the different regions, you have more data points in the regions that are going to have negative cross products. And you have very few data points here, and the data points aren't very far away from the mean of x and mean of y for those in regions 1 and 3, those regions in which you'd expect a positive cross product. So this just reflects the fact that you're going to have a negative linear relationship. When we have a positive linear relationship in a scatter plot, you're going to have more data points in regions 1 and 3. You're going to have more data points in those regions in which you have positive cross products. That should make intuitive sense, because here you have a positive linear relationship, you're going to have more positive cross products. When we have sort of a cloud of data points, there's no apparent linear relationship, you're going to have data points that are in roughly equal proportions in all of these different regions. So it's that calculation of the covariance, it's not going to capture any apparent linear relationship. You can see the negative cross products and the positive cross products, they all kind of cancel each other out. They're all kind of equally spaced in these different regions. If we look at a nonlinear relationship, a relationship that doesn't look like a straight line, you can see that what's going to happen when we have a nonlinear relationship is that you're going to have often points that are kind of in all four quadrants. And this is going to capture no apparent linear relationship because you can see that the regions in which we have negative cross products and the regions in which we have positive cross products, they're all going to have a roughly equal number of data points with roughly equal deviations from the mean of x and the mean of y. So let's look at our data set of body fat percentage and weight. This is again a set of individuals, and we have people's body weight in pounds and their body fat percentage. So if we look at our summary statistics again, we can see that we have a mean of x, which is 18.6. So the average body fat percentage is 18.6% in this data set. And then we have weight in pounds. The average weight in pounds is about 177. We can look at our scatter plot and we can plot the mean of x and the mean of y. We have four quadrants, 1, 2, 3, and 4. For these different quadrants, you can eyeball and you can see that, well, actually, it looks like there are more data points in the regions in which we'd expect positive cross products, meaning regions 1 and 3. And not only that, those points in those regions, they tend to be pretty far away. There are quite a few observations that are really far away from the mean of x and mean of y. If you look at the regions 2 and 4, those regions in which we expect a set of negative cross products, there aren't as many data points, and the data points in general tend to be a little bit closer to the mean of x and the mean of y. This reflects the fact that there is, in general, a kind of positive linear relationship in the set of data. And in fact, when we calculate the covariance of x and y using statistical software, you wouldn't expect to do this kind of calculation by hand. There are too many data points. And often researchers do use statistical software to calculate the covariance of data sets. But when we do that calculation, we find the covariance is about 140.8. That should make intuitive sense because a positive covariance suggests a positive linear relationship. Right? And now as an aside, I should say, we've talked about variance of x, variance of y, and we've talked about now the covariance of x and y. How are these, in fact, related? Well, you can think of the covariance of a variable with itself as, in fact, the variance of a variable, and this can be seen quite easily. Here's the formula for the covariance in a sample between x and y. Well, what happens when we consider, instead of y minus y bar, we replace x minus x bar? So in essence, what we're doing is we plug in x for y, and we have this calculation that is equivalent to the variance of x. So you can see that one way to think about variance is, in fact, the covariance of a variable with itself. Variance of x, variance of y, and the covariance of an x and y are, in fact, related in this way. One important point about covariance is in terms of the units. As I mentioned earlier, covariance is given in the units of x and y, so body fat percentage times weight in pounds. A related point is that covariance, because it's expressed in the units of x and y, it actually only gives us the sign of the linear relationship. It's because covariance, it depends, the actual value of covariance numerically depends on the units used. So for example, in this instance of body fat percentage and weight, we found the covariance is 140.8, right? Well, suppose we multiply pounds by 5, and then so a person who weighs 100 pounds now is given a value of 500 pounds arbitrarily. Well, the original covariance is expressed in 140.8 body fat percentage times weight in pounds. Okay, those are the units. Well, what happens when we multiply weight in pounds arbitrarily by 5? It's not going to fundamentally change at all the relationship between x and y. But what will happen is that the covariance will inflate by a factor of 5. The covariance is now 140.8 times 5, which is now 704. This is a big problem with covariance because you can see that If you get a value of covariance that you think is small, you can just arbitrarily multiply one of your variables by some factor. So suppose you get a covariance of 2, and you want to impress your reviewers or other researchers, and you multiply your units by 100, you get a covariance of 200. Covariance only gives you the sign or direction. It does not give you the magnitude or strength of a relationship. So things to know so far about covariance. We can think of covariance as based on a scatter plot, except you're reorienting the data points in relationship to the mean of x and the mean of y, rather than the overall dimensions of x and y. Scatter plots we can use to intuitively understand the relationship between two variables, but covariance is used to quantify some apparent relationship in a scatter plot. Covariance gives us the direction of a linear relationship between two variables, and by linear relationships we mean what appear to be straight line patterns in scatter plots. Covariance can take on any number, but it's expressed in the units of the two variables, and the magnitude of covariance depends on the units of the two variables, so covariance cannot actually give us the size or strength of relationship between two variables. It can only give us the direction. And with that, we've concluded our discussion of covariance as a measure of association for two numerical variables.